Right now, as you're watching this, Saturn is gracefully rotating 746 million miles away, its magnificent rings catching sunlight like a cosmic chandelier. We thought we understood why some planets have rings and others don't. We were completely wrong. What we've discovered about Saturn's rings versus Jupiter's mysterious lack of them reveals one of the most mind-bending stories in our solar system. A tale of cosmic violence, impossible timing, and gravitational forces so precise they seem almost designed. For decades, astronomers believed ring formation was simple. Debris from shattered moons, captured asteroids, leftover material from planetary formation. The bigger the planet, the more impressive the rings should be. Jupiter, our solar system's undisputed giant, containing more mass than all other planets combined, should have the most spectacular ring system imaginable. Instead, it has virtually nothing. 4 gossamer threads of dust so faint they weren't discovered until 1979. So pathetic they're barely worth mentioning. Meanwhile, Saturn, less than 1/3 Jupiter's mass, sports the most magnificent ring system we've ever encountered. Rings so vast they stretch 175,000 miles from edge to edge, nearly the distance from Earth to our moon. Rings so complex they contain thousands of individual ringlets, shepherd moons, spokes that appear and disappear, and structures that shouldn't exist according to our understanding of orbital mechanics. The Cassini spacecraft, during its 13-year intimate dance with Saturn, transmitted back data that revolutionized everything we thought we knew. These aren't ancient relics from the solar system's birth. They're impossibly young, perhaps younger than the dinosaurs. They're not stable structures peacefully orbiting for eons. They're dynamic, violent, constantly being born and destroyed. And most disturbing of all, they might be temporary visitors we're witnessing during a cosmic blink of an eye. Tonight, we're diving deep into one of astronomy's most beautiful mysteries. We'll discover how gravitational resonances can both create and destroy ring systems. We'll explore why Jupiter's immense gravity, instead of gathering more material, actually prevents ring formation. We all witness the violent birth of Saturn's rings and understand why you and I are living during the precise moment in cosmic history when they exist. Dr. Linda Spilker, Cassini project scientist, spent decades studying these structures. Her team's discoveries forced us to rewrite textbooks and question fundamental assumptions about planetary ring systems. The story they uncovered isn't just about ice and rock. It's about chaos and order, creation and destruction, and the delicate balance that makes cosmic beauty possible. What makes this mystery even more captivating is what it reveals about observation bias. We assume Jupiter should have rings because of its size. We never questioned why Saturn's rings are so perfect, so precisely organized, so impossibly thin, just 30 feet thick despite spanning a distance equivalent to 2/3 the Earth-Moon separation. We never wondered why ring systems are so rare when debris is so common. As we explore this cosmic puzzle together, we'll uncover why ring formation requires a perfect storm of circumstances, the right kind of moon, in the right location, experiencing the right kind of destruction at the right moment in planetary history. We'll understand why Jupiter's moons are too big, too far away, and too stable to create the spectacular display we see around Saturn. If you're fascinated by the hidden forces that shape our cosmic neighborhood, subscribe and hit that thumbs up. And here's a mind-bending question. If you could witness any moment in Saturn's history, would you choose to see the violent birth of its rings, or would you return 100 million years from now to witness their final disappearance? Comment below. I'll pin the most thought-provoking response. The story begins not with rings themselves, but with the fundamental forces that govern what can exist around a massive planet. Every world in our solar system sits within invisible boundaries that determine the fate of any object that ventures too close. Understanding these cosmic danger zones is the key to unlocking why Saturn became a jeweled giant, while Jupiter remained disappointingly bare. Now let's begin this journey into the gravitational architecture of our solar system. Chapter 1. Roche limits. Every massive object in the universe creates an invisible sphere of destruction around itself. A boundary where the laws of physics become executioner to any moon or asteroid unfortunate enough to wander too close. This gravitational killing field is called the Roche limit, named after French mathematician Édouard Roche, who calculated these cosmic death zones in 1848. Understanding this fundamental boundary is the first key to solving why Saturn hosts cosmic magnificence while Jupiter remains eerily bare. Picture a small moon orbiting peacefully around a planet. The moon holds together because its own gravity pulls all its material toward the center. But as this moon spirals closer to the planet, perhaps through tidal friction, gravitational perturbations, or orbital decay, something sinister begins to happen. The planet's gravity starts pulling harder on the moon's near side than its far side. This difference in gravitational force creates tidal stress. Initially, the moon can resist. Its internal gravity, though weak compared to the planet, keeps its material bound together. But there is a critical distance where the planet's tidal forces become stronger than the moon's self-gravity. Cross this line, and physics delivers its verdict: total destruction. The moon doesn't simply fall into the planet. It disintegrates, torn apart particle by particle, transformed from a solid world into a swarm of debris. For a fluid body orbiting Earth, this distance sits at approximately 2.44 times Earth's radius, about 15,500 kilometers from our planet's surface. For solid rocky bodies, slightly closer at 2.44 times the planet's radius. But here's where the story becomes fascinating. Different planets have dramatically different Roche limits, and these differences hold the secret to understanding ring systems. Saturn's Roche limit extends to roughly 147,000 kilometers from its center, about 2.44 times Saturn's radius. Notice something remarkable? Saturn's magnificent ring system stretches from 7,000 to 80,000 kilometers from the planet's surface, placing the entire structure well within Saturn's Roche limit. This isn't coincidence. It's the fundamental requirement for stable ring formation. Material within the Roche limit cannot coalesce into larger moons. Gravity prevents any significant accretion. Instead, countless small particles orbit independently, colliding and fragmenting, grinding each other down to smaller and smaller pieces. This creates a self-maintaining population of ring material. Fresh debris, constantly replenishing what gets lost to atmospheric drag or other processes. Jupiter's Roche limit tells a different story. Extending to approximately 175,000 kilometers from Jupiter's center, it creates a much larger zone where ring material could theoretically exist. Jupiter should have more space for impressive rings than Saturn does. Instead, it is almost nothing. Just 4 tenuous rings composed mainly of dust particles, so faint they're invisible to ground-based telescopes. The Voyager missions revealed Jupiter's pathetic ring system in 1979, shocking astronomers who expected something more substantial around such a massive planet. The main ring, consisting primarily of material blasted off Jupiter's inner moons, Adrastea and Metis, by micrometeorite impacts, extends from 129,000 to 182,000 kilometers from Jupiter's center. Additional gossamer rings, fed by dust from Amalthea and Thebe, stretch even farther outward. But these structures barely qualify as rings. They're more like extended dust clouds, lacking the density, organization, and spectacular visual impact of Saturn's system. The total mass of Jupiter as rings is estimated at roughly 8 kilograms. Sounds impressive until you realize Saturn's rings contain about 8 kilograms of material, roughly 100 million times more massive. To put this in perspective, if Saturn's rings were compressed into a single moon, it would create a world about 500 kilometers in diameter, larger than many significant asteroids. Jupiter's rings, compressed similarly, would form an object perhaps 10 kilometers across, smaller than most city-destroying asteroids we monitor for Earth impact potential. The Roche limit alone doesn't explain this dramatic difference. Both planets have substantial zones where ring material could exist. Both have moons that orbit within or near these zones. Both experience meteorite bombardment that could supply ring material. Yet their ring systems couldn't be more different. The answer lies not just in where rings can exist, but in how they form and what forces shape their evolution. Modern computational models reveal that ring formation requires a perfect balance of destruction and replenishment. Too little source material, and rings fade away within millions of years. Too much gravitational disturbance from large moons, and ring material gets scattered or absorbed. Too much planetary magnetic field interference, and charged particles get swept away. Too little, and solar wind gradually erodes the system. Saturn sits in a gravitational sweet spot. Its Roche limit is large enough to accommodate substantial ring material, but not so large that gravitational perturbations from distant moons destabilize the system. Its rotation rate creates magnetic field effects that help shepherd ring particles. Its atmospheric density provides just enough drag to clean up stray material without destroying the main ring structure. Consider this remarkable fact. Saturn's rings are incredibly thin relative to their width. The main ring system spans roughly 65,000 kilometers, but averages only 30 feet thick, a ratio equivalent to a sheet of paper scaled to the width of a football field. This extreme thinness requires precise gravitational control, with countless interactions between ring particles, moons, and Saturn itself, maintaining the structure's stability. Jupiter's environment tells a different story. Its rapid rotation creates powerful magnetic fields that interact violently with charged particles. Its large moon system creates complex gravitational resonances that destabilize ring material. Its intense radiation environment charges dust particles, making them susceptible to electromagnetic forces that can eject them from stable orbits. The Galilean moons, Io, Europa, Ganymede, and Callisto, orbit beyond Jupiter's main Roche limit, but their gravitational influence extends inward, creating orbital resonances that sweep clean much of the space where substantial rings might form. These moons act like cosmic vacuum cleaners, gravitationally stirring any ring material into unstable orbits that either impact Jupiter or get ejected from the system. What emerges is a picture of planetary ring systems as delicate temporary structures that exist only under very specific conditions. The Roche limit defines where they can exist, but formation requires the right kind of source material delivered at the right time, with just the right amount of gravitational sculpting from nearby moons, and protection from destructive processes that would otherwise sweep the system clean. As we've seen, both Jupiter and Saturn have Roche limits that could accommodate impressive ring systems. The presence or absence of rings isn't simply about gravitational boundaries. It is about the complex interplay of forces that determine whether ring material can accumulate, survive, and evolve into the organized structures we observe. The next piece of our puzzle lies in understanding how these ring systems actually form, and why the process might be far more violent and recent than anyone ever imagined. Chapter 2. Violent Origins. The birth of Saturn's rings was not a gentle process. Recent evidence suggests we're witnessing the aftermath of a cosmic catastrophe, a moon destroyed so violently and so recently that the rings we see today are essentially crime scene. Evidence from one of the most spectacular acts of gravitational violence in our solar system's recent history. This revelation has fundamentally changed how astronomers think about ring formation and helps explain why Jupiter's environment has failed to produce anything comparable. For decades, scientists assumed Saturn's rings were ancient primordial remnants left over from the planet's formation 4.6 billion years ago. This made intuitive sense. Such a massive, organized structure surely required eons to develop. The intricate patterns, the thousands of individual ringlets, the complex resonance structures, all suggested a system that had evolved slowly over cosmic timescales. The Cassini spacecraft shattered this comfortable assumption. During its grand finale phase in 2017, Cassini dove between Saturn's rings and atmosphere, measuring the ring's mass with unprecedented precision. The results were startling. Saturn's rings contain far less material than expected, suggesting they're much younger than the planet itself. Current estimates place their age between 100 and 400 million years, practically yesterday in cosmic terms. This finding revolutionized ring science because it meant Saturn's rings formed during the age of dinosaurs on Earth, not during the solar system's violent birth. Something catastrophic happened relatively recently in Saturn's neighborhood, and we're fortunate enough to exist during the brief cosmic moment when the aftermath remains visible. But what kind of event could create such a spectacular display? The most compelling scenario involves the destruction of a large moon, perhaps comparable in size to Mimas or Enceladus, that once orbited Saturn in the region where we now see rings. This moon, which scientists have nicknamed Chrysalis, met its doom through a process called tidal disruption. As orbital mechanics slowly caused it to spiral inward toward Saturn, it crossed the fatal Roche limit we discussed earlier. Imagine witnessing this cosmic execution. The doomed moon, roughly 600 kilometers in diameter, approaches Saturn's Roche limit over thousands of years. Tidal forces gradually elongate its shape, pulling it into an egg-like form. Massive earthquakes crack its surface as internal stresses exceed the strength of rock and ice. Finally, as it crosses the critical distance, the moon begins to disintegrate. The destruction wouldn't be immediate. First, surface material would peel away like layers of an onion, creating streams of debris that spread around Saturn in orbital paths matching the original moon's trajectory. The moon's core might survive several orbits, gradually shedding material with each pass, creating multiple debris streams that would eventually merge and spread into a disk-like configuration. Computer simulations of this process reveal fascinating details. Dr. Robin Canop's team at Southwest Research Institute modeled the destruction of various moon compositions and sizes. They found that an icy moon rich in water ice, similar to many of Saturn's existing moons, would create debris patterns remarkably similar to Saturn's ring structure. The ice content explains the ring's high reflectivity and distinctive appearance. But ring formation requires more than just moon destruction. The debris must spread efficiently around the planet without clumping back together or falling into Saturn's atmosphere. This spreading process involves complex gravitational interactions with Saturn's remaining moons, particularly those that survived outside the destruction zone. These moons act as gravitational shepherds, sculpting the ring material into organized structures. The timing of this catastrophe might not have been random. Recent research suggests the destruction of Chrysalis could have been triggered by orbital resonances with other moons in Saturn's system. As moons slowly migrate outward due to tidal forces, they occasionally pass through resonant configurations that pump energy into their orbits, potentially driving one moon inward toward destruction while ejecting others outward. This resonance scenario explains another puzzling feature of Saturn's system: the unusual orbit of Iapetus, Saturn's third largest moon. Iapetus orbits at an oddly large distance with an unusual inclination, as if it was once part of a more tightly packed moon system that experienced violent reorganization. The same event that destroyed Chrysalis might have flung Iapetus into its current distant orbit. Jupiter's environment tells a dramatically different story. The Galilean moons Io, Europa, Ganymede, and Callisto formed in a stable resonance chain that has persisted for billions of years. Io completes exactly 4 orbits for every 2 of Europa and every 1 of Ganymede, creating a gravitational lock that prevents the kind of chaotic interactions that could drive moons toward destruction. Moreover, Jupiter's intense magnetic field and radiation environment would quickly destroy any ring material from a disrupted moon. Charged particles in Jupiter's magnetosphere interact violently with dust and ice, either sputtering material away or causing it to spiral into the planet. Any rings formed by moon destruction would be short-lived, surviving perhaps only thousands of years rather than the hundreds of millions required to build Saturn's spectacular system. The differences extend to the types of moons available for destruction. Saturn's inner moon system contains numerous small, icy bodies that could serve as ring material sources. These moons are composed largely of water ice with some rocky material, perfect for creating the reflective, long-lasting ring particles we observe. Jupiter's inner moons are smaller, denser, and more rock-dominated, less suitable for spectacular ring formation. Recent discoveries have added another layer to this story. The Cassini mission detected complex organic molecules in Saturn's rings, suggesting the destroyed moon might have contained organic compounds, perhaps even a subsurface ocean like those found on Enceladus and Titan. This raises the remarkable possibility that Saturn's rings contain the scattered remains of a world that once harbored conditions suitable for life. The violence of ring formation also explains their dynamic nature. Saturn's rings aren't static structures. They're constantly evolving, with material migrating inward due to various drag forces, while new material gets replenished through ongoing collisions and gravitational stirring. Cassini observed spokes, radial features that appear and disappear on timescales of hours, suggesting electromagnetic effects continue to shape the ring system. Understanding this violent origin story changes how we view planetary ring systems throughout the universe. Rather than being common, long-lived features, substantial ring systems might be rare, temporary displays that we're privileged to witness during brief windows of cosmic time. Most planets that experience moon destruction would quickly lose their ring material to various dissipative processes. This rarity makes Saturn's rings even more precious. We exist during a cosmic moment when gravitational violence has created temporary beauty, a celestial accident that transforms an ordinary gas giant into one of the most visually stunning objects in our solar system. In a few 100 million years, as ring material continues to spiral into Saturn's atmosphere, this spectacular display will fade, leaving future civilizations to wonder what once graced our solar system's second-largest planet. The story of violent origins leads us naturally to our next mystery: how the scattered debris from moon destruction organizes itself into the incredibly complex, structured system we observe today. The rings aren't just random collections of particles. They're architectural marvels of gravitational engineering, shaped by forces so subtle and precise, they seem almost impossibly designed. Understanding this organizational process reveals why Jupiter's environment, despite its immense gravitational power, has failed to create anything approaching Saturn's magnificent display. Chapter 3: Shepherd Moons. The magnificent organization of Saturn's rings, their razor-sharp edges, distinct gaps, and intricate braided structures, doesn't arise by chance. These features are sculpted by an invisible army of gravitational architects, tiny moons that orbit within and around the ring system, using their modest gravity to shepherd billions of ring particles into organized patterns. Understanding how these shepherd moons operate reveals why Saturn's rings achieve such spectacular complexity, while Jupiter's sparse ring system remains chaotically disorganized. Picture Pandora and Prometheus, two small moons that flank Saturn's narrow F-ring like cosmic border guards. Pandora, just 84 kilometers across, orbits slightly outside the ring, while Prometheus, 86 kilometers in diameter, patrols the inner edge. These modest worldlets, each smaller than most Earth cities, collectively control the behavior of countless ring particles through their gravitational influence. The F-ring itself demonstrates the delicate precision required for ring shepherding. At only 50 kilometers wide, but stretching 300,000 kilometers around Saturn, This structure maintains its narrow width through constant gravitational correction from its guardian moons. When ring particles drift too far inward, Prometheus nudges them back outward. When they stray too far outward, Pandora gently guides them inward. This cosmic ballet has continued for millions of years. But the shepherding process involves more than simple gravitational nudging. As Prometheus orbits faster than the F-ring particles, being closer to Saturn, it periodically overtakes sections of the ring, creating spectacular disturbances. During these encounters, the moon's gravity strips material from the ring, creating streamers and braids that spiral around the ring structure. These interactions were captured in stunning detail by Cassini, revealing a dynamic system constantly reshaping itself. The mathematics of gravitational shepherding reveal the incredible precision required. Each shepherd moon must orbit at exactly the right distance to maintain ring confinement without destroying the structure entirely. Too close, and the moon's gravity would tear the ring apart. Too far, and ring particles would spread chaotically outward. The stable orbits we observe represent solutions to complex multi-body gravitational equations that took nature millions of years to perfect. Saturn's ring system contains multiple examples of shepherd moon architecture. Atlas, a 37-kilometer moon, maintains the sharp outer edge of the A-ring through gravitational resonances. Daphnis, only 8 kilometers across, orbits within the Kilo gap of the A-ring, creating spectacular propeller-shaped wakes as it gravitationally stirs nearby particles. Each of these tiny moons punches far above its weight class in terms of gravitational influence. The most remarkable shepherd moon story involves Mimas, Saturn's Death Star look-alike moon. Orbiting far outside the ring system, Mimas seems too distant to affect ring particles directly. Yet its gravitational influence creates the most prominent feature in Saturn's rings, the Cassini division, a 4,700-kilometer gap between the A and B rings. This gap exists because any particle orbiting there would complete exactly 2 orbits for every 1 orbit of Mimas, a 2-to-1 resonance that gradually removes material from that region. Resonances represent one of the most elegant aspects of celestial mechanics. When a ring particle's orbital period becomes a simple fraction of a moon's period, like 2-to-1, 3-to-2, or 4-to-3, the particle experiences repeated gravitational tugs at the same point in its orbit. Over thousands of orbits, these tugs accumulate, either pumping energy into the particle's orbit, causing it to spiral outward, or removing energy, causing inward spiral. The result is cleared gaps at specific distances from Saturn. Jupiter's ring system lacks this intricate shepherding architecture entirely. While Jupiter has 4 small inner moons, Metis, Adrastea, Amalthea, and Thebe, that interact with its tenuous rings, these interactions produce chaos rather than organization. The moons continuously blast ring material with micrometeorite impacts, creating dust that spreads randomly throughout the system rather than forming organized structures. The fundamental difference lies in the stability and positioning of moon systems. Saturn's inner moons occupy relatively stable orbits at just the right distances to create constructive gravitational interactions with ring material. Many of these moons likely formed from ring material that managed to accrete outside the main ring zones, creating a self-organizing system where rings and moons evolve together. Jupiter's inner moons tell a different story. Subjected to intense tidal heating from Jupiter's massive gravity and bombarded by high-energy particles in Jupiter's radiation belts, these moons are gradually being destroyed rather than providing stable gravitational anchors for ring organization. Io, the most famous example, continuously resurfaced by volcanic activity driven by tidal flexing, while the smaller inner moons slowly lose material to space. The shepherding process also requires the right kind of ring material. Saturn's rings consist primarily of water ice particles ranging from tiny grains to house-sized boulders. This material responds predictably to gravitational forces and maintains its reflectivity over time, creating the bright, organized structures we observe. The ice composition also allows particles to stick together during gentle collisions, enabling the formation of temporary clumps that can be shepherded more effectively. Jupiter's ring material consists mainly of fine dust blasted off its inner moons by micrometeorite impacts. This dust has very different properties than Saturn's ice particles. It's easily affected by electromagnetic forces, responds unpredictably to gravitational shepherding, and gradually darkens over time as radiation damage accumulates. These characteristics make organized ring structures extremely difficult to maintain, even if adequate shepherding were available. Recent Cassini observations revealed the sophisticated nature of shepherding interactions. The mission captured video footage of propeller-shaped features in Saturn's rings, disturbances created by small moonlets embedded within the ring material itself. These moonlets, too small to be seen directly, reveal their presence through gravitational wakes that persist for hundreds of kilometers. They represent an intermediate stage between individual ring particles and full shepherd moons. The temporal aspect of shepherding adds another layer of complexity. Shepherd moons gradually migrate outward due to tidal interactions with Saturn, meaning the current ring architecture is temporary. Computer models suggest that in the past, different moons may have occupied shepherding roles, creating different ring structures that have since evolved or disappeared. This dynamic evolution helps explain why ring systems are rare. They require not just initial formation, but ongoing maintenance by appropriately positioned moons. Understanding shepherd moon dynamics has revolutionary implications for exoplanet research. As we discover planetary systems around other stars, the presence or absence of ring systems could indicate the stability and organization of moon systems. Complex rings might signal mature planetary systems with stable moon populations, while chaotic or absent rings could indicate young systems still undergoing violent reorganization. The precision required for effective shepherding also highlights the remarkable nature of Saturn's current configuration. Multiple moons must occupy exactly the right orbits to create the ring structures we observe. The probability of achieving this arrangement by chance is vanishingly small, suggesting that Saturn's rings and moons represent a mature, evolved system that has had millions of years to reach gravitational equilibrium. Consider the engineering marvel this represents. Billions of tons of material organized into structures thinner than a skyscraper is tall yet spanning distances greater than the Earth-Moon separation, all maintained by the gravitational influence of moons no larger than small asteroids. The precision rivals human-engineered systems, yet operates through purely natural processes guided by fundamental physics. Jupiter's inability to create similar shepherding architecture stems from its fundamentally different environment. Its massive gravity creates steep gravitational gradients that make stable moon orbits difficult to maintain within ring-forming regions. Its powerful magnetic field accelerates charged particles to high energies that damage both ring material and potential shepherd moons. Its large moon system creates complex resonances that destabilize rather than organize ring material. The shepherding moon story reveals that ring formation requires more than just source material and gravitational boundaries. It demands a supporting cast of small moons, positioned at exactly the right distances to provide ongoing gravitational sculpture. Saturn won this cosmic lottery, creating a system where destruction and organization work together to produce temporary beauty. Jupiter, despite its immense power, lacks the delicate gravitational architecture necessary to transform chaos into cosmic art. Chapter 4. Cassini Division Standing. Out in Saturn's ring system, like a cosmic highway divider, is the Cassini division, a 4,700-kilometer gap that separates the bright A and B rings with mathematical precision. This seemingly empty space reveals one of the most elegant examples of gravitational resonance in our solar system, and understanding its creation helps explain why Jupiter's chaotic environment cannot produce similar organized structures. The Cassini division represents the perfect balance between destruction and preservation that makes Saturn's rings possible. Named after Giovanni Cassini, who first observed this gap through telescopes in 1675, the division initially appeared to be completely empty space. Modern spacecraft have revealed a more complex reality. The gap contains sparse ring material, but at densities roughly 100 times lower than the surrounding bright rings. This sparse population exists in a state of constant gravitational stress, never able to accumulate into the dense structures seen elsewhere. The creator of this magnificent gap orbits far from the rings themselves. Mimas, Saturn's innermost major moon, circles the planet every 22.6 hours at a distance of 185,520 kilometers from Saturn's center. Any ring particle orbiting at the location of the Cassini division completes exactly 2 orbits for every 1 orbit of Mimas, a 2-to-1 orbital resonance that creates devastating consequences for ring material attempting to occupy that zone. To understand how this resonance works, imagine a ring particle innocently orbiting within what would become the Cassini division. Initially, its orbit appears stable, circling Saturn every 11.3 hours. But Mimas lurks in the distance, and every 22.6 hours, precisely every 2 particle orbits, Mimas reaches the same relative position to the particle. This creates a periodic gravitational tug that occurs at the exact same point in the particle's orbit. Individual gravitational interactions between Mimas and ring particles are incredibly weak. Mimas, though one of Saturn's larger moons, contains only about 1/50,000th the mass of our moon. At a distance of over 100,000 kilometers, its gravitational influence on individual ring particles seems negligible. But resonances have a remarkable property. Small periodic forces can accumulate enormous effects over time. Each time Mimas passes overhead, it gives the ring particle a tiny gravitational push. Since this push always occurs at the same point in the particle's orbit, the effects accumulate rather than canceling out. Over hundreds of thousands of orbits, these tiny nudges pump energy into the particle's orbit, gradually increasing its eccentricity and inclination until the orbit becomes unstable. The mathematical beauty of this process lies in its selectivity. Only particles at the exact 2-to-1 resonance distance experience this cumulative effect. Particles slightly closer or farther from Saturn have different orbital periods, so Mimas doesn't push them consistently at the same orbital position. They experience random gravitational tugs that average to 0 over time, leaving their orbits stable and undisturbed. Computer simulations reveal a timeline of gap formation. Starting from a uniform ring distribution, the 2-to-1 resonance begins clearing material within about 100 million years. The process is an immediate annihilation. Particles gradually gain orbital eccentricity until their paths cross other ring regions or become so elongated they either impact Saturn or get ejected from the system entirely. The gap deepens over time as more material gets removed. But the Cassini division isn't completely empty, and this partial population reveals another layer of complexity. Some material remains in the gap, occupying special orbital configurations that avoid the worst effects of the 2-to-1 resonance. These particles exist in what mathematicians call stable islands, specific combinations of orbital elements that allow survival in otherwise hostile gravitational territory. The sparse ringlets within the Cassini division showcase nature's ability to find order within chaos. The most prominent feature, the Huygens ringlet, maintains its structure through complex interactions between resonance effects, particle collisions, and electromagnetic forces. Material in this ringlet experiences the same 2-to-1 resonance with Mimas, but maintains stability through precise orbital geometry that minimizes cumulative perturbations. Jupiter's ring system demonstrates what happens when resonance effects work without the organizational benefits seen at Saturn. Jupiter's large moons create numerous resonances throughout the region where substantial rings might form, but these resonances primarily act destructively. Instead of carving elegant gaps in dense ring systems, they prevent ring material from accumulating in the first place. The fundamental difference lies in the starting conditions and environmental factors. Saturn's rings formed as a dense system that resonances could then sculpt and organize. Jupiter's environment prevents dense ring formation initially, so resonances simply remove the little material that does accumulate. It is the difference between a sculptor carving beautiful forms from marble versus trying to sculpture with sand that keeps blowing away. The Cassini division also reveals the temporal evolution of ring systems. The gap hasn't existed for the entire 4.6 billion year history of the solar system. It formed only after ring material accumulated sufficiently for Mimas's resonance to begin effective clearing. Before ring formation, the space now occupied by the Cassini division was simply empty. After ring destruction in the distant future, it will be empty again, but for different reasons. Mimas itself tells part of this story. The moon bears a massive crater, Herschel crater, that gives it a distinctive Death Star appearance. This crater, 130 kilometers across on a moon only 400 kilometers in diameter, likely formed from an impact that nearly shattered Mimas entirely. Had that impact been slightly more violent, it might have destroyed Mimas, eliminating the 2-to-1 resonance and allowing ring material to fill what is now the Cassini division. The preservation of the Cassini division requires ongoing maintenance. Ring material continuously tries to diffuse into the gap through various processes: collisional spreading, electromagnetic effects, gravitational stirring by smaller moons. But Mimas's resonance acts like a cosmic broom, continuously sweeping away material that ventures into the forbidden zone. This dynamic balance between invasion and removal maintains the gap's sharp edges. Modern observations have revealed subtle variations in the Cassini division structure that provide clues about ring dynamics. The gap's edges show wave-like patterns created by gravitational resonances with smaller moons. Density variations within the sparse material follow patterns that correlate with electromagnetic effects from Saturn's magnetic field. These details help astronomers understand how multiple forces work together to shape ring architecture. The division also serves as a natural laboratory for studying particle dynamics in low-density environments. Unlike the dense main rings where particle interactions dominate behavior, material in the Cassini division experiences primarily individual particle motion modified by Saturn's gravity and magnetic field. This allows scientists to study fundamental processes that are masked by complexity in denser ring regions. Recent discoveries have added new mysteries to the Cassini division story. Cassini spacecraft observations revealed temporary features that appear and disappear within the gap, structures that shouldn't be able to maintain themselves given the hostile resonance environment. These transient phenomena suggest that ring dynamics involve processes we don't yet fully understand, possibly related to electromagnetic effects or gravitational interactions with undiscovered small moons. The precision required to maintain the Cassini division highlights the delicate nature of ring systems. Small changes in moon orbits, planetary rotation, or magnetic field strength could alter the resonance characteristics and change the gap's properties. The current configuration represents a temporary equilibrium that will evolve as Saturn's moon system continues its slow outward migration. Understanding the Cassini division has profound implications for interpreting ring systems around other planets and exoplanets. The presence of gaps and complex structures in ring systems indicates mature gravitational architecture with stable moon populations. Chaotic or gap-free rings might signal young systems still evolving toward organized configurations. The mathematical elegance of the 2-to-1 resonance that creates the Cassini division represents one of the most perfect examples of celestial mechanics in our solar system. It demonstrates how simple gravitational laws, operating over cosmic timescales, can produce structures of breathtaking regularity and beauty. The gap stands as a testament to the hidden order underlying apparent chaos in planetary systems. Jupiter's inability to produce similar resonance-carved structures isn't a failure of physics. It is a consequence of environmental conditions that prevent the accumulation of dense ring material in the first place. The Cassini division exists because Saturn achieved the perfect balance of ring formation and gravitational sculpting that Jupiter's more violent environment makes impossible. This gap in Saturn's rings represents not just empty space, but the cosmic precision required to create lasting beauty in our solar system. Chapter 5. Ring Composition. The material that forms planetary rings determines not just their appearance, but their ability to survive and evolve into the spectacular structures we observe. Saturn's rings shine brilliantly because they're composed primarily of pure water ice, pristine, reflective, and surprisingly durable in the hostile environment of space. Jupiter's rings remain nearly invisible because they consist of dark, fine dust particles that absorb rather than reflect sunlight. This fundamental difference in composition explains much about why these two ring systems developed such dramatically different characteristics. Water ice wasn't an obvious choice for ring material when scientists first began studying Saturn's rings. Early observations suggested the rings might be composed of rocky debris, metal fragments, or even solid ammonia, all materials that seemed more likely to survive in the radiation environment around a massive planet. The discovery that Saturn's rings are roughly 99% pure water ice revolutionized our understanding of ring formation and evolution. The purity of Saturn's ring ice is remarkable. Spectroscopic analysis reveals water signatures so clean they rival the purest laboratory samples. This purity wasn't accidental. It results from processes that preferentially preserve ice while removing contaminating materials. When meteorites impact ring particles, they vaporize the dark rocky components while leaving ice chunks largely intact. Solar radiation sublimates surface contaminants but leaves the bulk ice structure unchanged. The size distribution of Saturn's ring particles reveals another crucial aspect of composition. Particles range from tiny grains smaller than sand to chunks the size of houses, with most falling in the range of centimeters to meters across. This size distribution maintains itself through a balance of collisional fragmentation and gravitational aggregation, processes that work effectively only with materials that have the right mechanical properties. Water ice possesses ideal characteristics for ring particle evolution. It's hard enough to maintain structural integrity during low-velocity collisions, but soft enough to fragment cleanly during high-energy impacts. Ice particles can stick together temporarily when they collide gently, allowing the formation of larger aggregates that enhance gravitational interactions. When these aggregates break apart, they create fresh, bright ice surfaces that maintain the ring's spectacular reflectivity. The temperature environment in Saturn's rings, averaging around -180 degrees Celsius, keeps water ice in its optimal state for ring formation. At these temperatures, ice behaves more like rock, maintaining sharp edges and distinct particle boundaries while remaining slightly compliant during collisions. Warmer temperatures would make ice too soft and sticky, causing rapid aggregation into larger moons. Colder temperatures would make ice too brittle, leading to rapid fragmentation into dust. Jupiter's ring composition tells a completely different story. Analysis of light scattered by Jupiter's rings reveals material dominated by silicate dust, tiny particles of rock and metal with sizes typically measured in microns. This dust originates primarily from micrometeorite bombardment of Jupiter's small inner moons, Metis, Adrastea, Amalthea, and Thebe. Each impact blasts microscopic fragments into space, where they spread into tenuous ring structures. The fundamental problem with dust as ring material lies in its electromagnetic properties. Dust particles become electrically charged through interactions with solar radiation and Jupiter's powerful magnetic field. Once charged, these particles experience electromagnetic forces that can overwhelm gravitational effects, making stable ring structures extremely difficult to maintain. Charged dust gets accelerated by magnetic fields, swept away by stellar winds, or forced into unstable orbits that end in planetary impact. Jupiter's intense radiation environment compounds the dust problem. High-energy particles in Jupiter's magnetosphere continuously bombard ring material, altering its surface chemistry and gradually sputtering material away into space. This process darkens already dark particles, making them even less reflective and more difficult to observe. The combination of electromagnetic acceleration and radiation sputtering gives Jupiter's ring particles lifetimes measured in thousands to hundreds of thousands of years, geological instants compared to the millions or hundreds of millions of years required for substantial ring development. The source mechanisms for ring material also differ dramatically between the two systems. Saturn's rings likely formed through the catastrophic destruction of a large, icy moon that provided enormous quantities of pure water ice all at once. This sudden delivery of homogeneous material allowed the formation of a dense, organized system that could evolve complex structures through gravitational and electromagnetic interactions. Jupiter's rings formed through ongoing bombardment of its small inner moons by interplanetary debris. This process delivers material continuously, but in tiny quantities, creating a sparse population of particles that never achieves the density required for complex gravitational interactions. The sporadic nature of bombardment also means ring density fluctuates randomly rather than evolving toward organized configurations. The mechanical properties of ring materials influence their evolution in subtle but important ways. Water-ice particles can undergo elastic collisions that redistribute energy without destroying particle integrity. This allows the development of velocity distributions that support wave phenomena, spiral density patterns, and other collective behaviors observed in Saturn's rings. Dust particles, in contrast, typically experience inelastic collisions that dissipate energy rapidly, preventing the development of organized structures. Recent Cassini measurements revealed unexpected complexity in Saturn's ring composition. While the rings are predominantly water ice, they contain trace amounts of organic compounds that give some regions a slight reddish tint. These organic materials likely originated from micrometeorite bombardment that delivered carbon-based compounds from the outer solar system. The organics concentrate in certain ring regions, suggesting dynamic processes that separate materials based on their properties. The presence of organic compounds in Saturn's rings raises fascinating questions about the composition of the destroyed moon that formed the ring system. If that moon contained organic materials, perhaps even a subsurface ocean with complex chemistry, then Saturn's rings represent the scattered remains of a world that might once have harbored conditions suitable for life. This possibility adds profound significance to understanding ring composition and evolution. Electromagnetic effects play crucial roles in determining how different ring compositions behave. Saturn's icy particles become weakly charged through photoelectric effects and plasma interactions, but their large size and high mass make them relatively immune to electromagnetic acceleration. They respond primarily to gravitational forces, allowing the development of stable, organized structures dominated by classical orbital mechanics. Jupiter's dust particles, being much smaller and lighter, become strongly charged relative to their mass. Electromagnetic forces can easily overcome gravitational attraction, making these particles behave more like components of a plasma than a gravitational system. This fundamental difference in force balance explains why Jupiter's rings remain chaotically disorganized while Saturn's achieve spectacular structure. The longevity of ring systems depends critically on their composition. Saturn's ice particles maintain their reflectivity through surface renewal processes that expose fresh ice during collisions. This self-cleaning mechanism allows the rings to remain bright and visible over geological timescales. Dark dust particles, once they accumulate radiation damage and surface contamination, have no mechanism for restoring their original properties. Temperature variations also affect different compositions differently. Saturn's rings experience temperature changes as they move into and out of Saturn's shadow during the planet's seasons. Ice particles respond to these changes by expanding and contracting slightly, but they remain structurally stable throughout the temperature range. Dust particles, particularly those containing metallic components, may undergo more dramatic thermal expansion that affects their charging properties and electromagnetic behavior. The gravitational self-organization observed in Saturn's rings requires particles with appropriate mechanical properties for collective behavior. Ice particles can transmit momentum efficiently through collisional cascades, allowing disturbances to propagate across large distances and enabling the development of spiral waves, density variations, and other large-scale structures. Fine dust lacks the mechanical coupling necessary for such collective phenomena. Understanding ring composition has broader implications for planetary science and astrobiology. The materials that form rings provide information about the composition of source bodies, moons, asteroids, or comets that supplied the ring material. Saturn's pure ice rings suggest a source body with substantial water content, possibly including subsurface oceans. Jupiter's rocky rings indicate source bodies with compositions similar to asteroids or the rocky components of comets. The preservation of different ring compositions also tells us about planetary environments. Saturn's ability to maintain ice rings over hundreds of millions of years indicates a relatively benign radiation environment compared to Jupiter's hostile magnetosphere. This information helps astronomers interpret ring systems around exoplanets and assess the habitability of moon systems in distant planetary systems. The stark difference in ring composition between Saturn and Jupiter ultimately explains much about their contrasting appearances and evolutionary paths. Saturn won the cosmic lottery by acquiring substantial quantities of reflective, mechanically suitable water ice delivered under conditions that allowed the formation of dense, stable ring structures. Jupiter's environment, despite its greater gravitational power, can only maintain sparse populations of dark dust that create barely visible structures subject to rapid destruction and renewal. This compositional story reveals that spectacular ring systems require not just the right gravitational conditions, but also the right materials delivered at the right time in planetary history. Saturn's magnificent rings exist because cosmic violence delivered the perfect building material to a planet with the ideal environment for long-term preservation and organization. Jupiter's sparse rings remind us that size and power alone cannot create cosmic beauty without the precise combination of materials and conditions that makes lasting structures possible. Chapter 6. Magnetic Shepherding. Invisible magnetic forces threading through. Saturn's rings create some of the most mysterious and beautiful phenomena in our solar system. Ephemeral spokes that appear and vanish like cosmic spirits, dancing across the ring plane in patterns that defied explanation for decades. Understanding how magnetic fields interact with charged ring particles reveals another crucial difference between Saturn's organized rings and Jupiter's chaotic system, showing how electromagnetic forces can either create intricate beauty or unleash destructive chaos. The discovery of Saturn's ring spokes came as a complete surprise during the Voyager missions in 1980 and 1981. These dark, radial features stretched across thousands of kilometers of ring material, appearing to rotate rigidly with Saturn's magnetic field rather than following the orbital mechanics that govern ring particle motion. The spokes violated everything astronomers thought they knew about ring behavior, creating features that seemed to ignore gravity in favor of some mysterious organizing force. Saturn's magnetic field. generated deep within the planet's interior by convecting metallic hydrogen, creates a complex three-dimensional structure around the planet. Unlike Earth's magnetic field, which is tilted relative to the rotation axis, Saturn's field aligns almost perfectly with the planet's spin. This unusual geometry means the magnetic field rotates like a rigid body, completing one rotation every 10 hours and 47 minutes, Saturn's internal rotation period. The mystery of the spokes lay in their behavior. Ring particles orbit Saturn according to Kepler's laws, with inner particles moving faster than outer ones. This differential rotation should quickly shear apart any radial structure, smearing it into a spiral pattern within hours. Yet the spokes maintain their radial orientation for hours at a time, somehow resisting the gravitational forces that should have destroyed them immediately. The solution came through understanding how tiny ring particles become electrically charged in space. Solar ultraviolet radiation strikes ring particles, knocking electrons from their surfaces through the photoelectric effect. Impacts from charged particles in Saturn's magnetosphere add or remove electrons. Even collisions between ring particles can transfer charge. These processes create a population of electrically charged dust grains mixed among the much larger, electrically neutral ice chunks that form the bulk of ring material. Once charged, microscopic ring particles experience electromagnetic forces in addition to gravity. These forces can be enormous compared to the particle's weight, easily strong enough to overcome gravitational attraction to Saturn. When Saturn's rotating magnetic field interacts with the charged particles, it can levitate them above the main ring plane, creating the dark radial features we observe as spokes. The physics of spoke formation involves a delicate balance between electromagnetic and gravitational forces. Only particles of specific sizes can be affected. Too large, and gravity overwhelms electromagnetic forces. Too small, and the particles get swept away entirely by magnetic field interactions. The optimal size range falls between about 0.1 and 2 microns in diameter, creating a population of fine dust that can be electromagnetically manipulated while remaining gravitationally bound to the ring system. Cassini's 13-year mission provided unprecedented observations of spoke dynamics, revealing their complex life cycle. Spokes typically form during Saturn's dawn, when photoelectric charging effects are strongest as ring particles emerge from Saturn's shadow into sunlight. They reach maximum visibility after several hours, then gradually fade as electromagnetic forces weaken and gravitational effects reassert dominance, causing the levitated particles to settle back onto the main ring plane. The seasonal variation of spoke activity provided crucial clues about their formation mechanism. Spokes are most prominent when Saturn's rings are viewed edge-on from the Sun, during equinox periods that occur every 15 Earth years. During these times, the Sun illuminates the rings at grazing angles, maximizing photoelectric charging effects while minimizing heating that could disrupt the delicate charge balance required for spoke formation. Jupiter's magnetic environment tells a radically different story. Jupiter's magnetic field is roughly 20 times stronger than Saturn's and tilted 11 degrees relative to the planet's rotation axis. This creates a much more violent electromagnetic environment where charged particles experience extreme acceleration and heating. Instead of gentle levitation effects that create organized structures, Jupiter's magnetic field acts like a cosmic particle accelerator, violently ejecting charged material from the ring region. The strength of Jupiter's magnetic field creates electromagnetic forces that overwhelm gravitational effects for particles, much larger than those affected at Saturn. This means not just fine dust, but substantial ring particles can be electromagnetically accelerated to escape velocities. Any significant population of charged particles gets swept away before it can accumulate into visible structures, preventing the formation of organized electromagnetic phenomena like Saturn's spokes. Jupiter's radiation environment compounds the electromagnetic chaos, High-energy electrons and protons, trapped in Jupiter's magnetic field, create radiation levels thousands of times more intense than those around Saturn. This radiation continuously bombards ring particles, altering their surface chemistry and charging properties in unpredictable ways. The rapid changes in particle charging prevent the stable electromagnetic interactions required for organized structure formation. The tilted geometry of Jupiter's magnetic field also disrupts potential electromagnetic organization. As Jupiter rotates, the magnetic field vector at any given location in the ring system changes direction, creating time-varying electromagnetic forces that prevent the formation of stable structures. This contrasts sharply with Saturn's aligned magnetic field, which provides a consistent electromagnetic environment that can support persistent features like spokes. Saturn's spoke phenomena reveal the sophisticated electromagnetic architecture of its ring system. The spokes don't just appear randomly. They form in response to specific triggers that scientists are still working to understand fully. Lightning activity in Saturn's atmosphere may provide electromagnetic pulses that initiate spoke formation. Impacts from interplanetary dust might create localized charging events that seed spoke development. Solar wind variations could modulate the electromagnetic environment enough to trigger spoke activity. Recent research has identified potential connections between spoke formation and Saturn's magnetospheric dynamics. The planet's magnetosphere, the region dominated by its magnetic field, experiences periodic compressions and expansions due to variations in solar wind pressure. These magnetospheric breathing events create electric fields that could drive the charge separation necessary for spoke formation, explaining why spoke activity varies on timescales comparable to solar wind disturbances. The electromagnetic interactions in Saturn's rings also influence their long-term evolution. Charged particles experience additional drag forces that cause them to spiral inward toward Saturn more rapidly than purely gravitational effects would predict. This electromagnetic drag provides a mechanism for ring material loss that supplements the better understood processes of atmospheric drag and gravitational perturbations. Understanding electromagnetic effects in ring systems has implications beyond our solar system. As astronomers discover ring systems around exoplanets, the presence or absence of electromagnetic phenomena could provide clues about planetary magnetic field strength and structure. Organized electromagnetic features might indicate stable, aligned magnetic fields, while chaotic or absent electromagnetic effects could signal tilted or variable magnetic environments. The spoke phenomenon also highlights the multiphysics nature of planetary ring systems. These aren't purely gravitational structures. They involve complex interactions between gravity, electromagnetism, plasma physics, and particle dynamics. Understanding ring behavior requires considering all these effects simultaneously, making ring systems some of the most complex dynamical systems in planetary science. Modern computer simulations of ring electromagnetic effects require enormous computational resources to capture the range of physical processes involved. Particles must be tracked individually to account for their varying charge states and sizes, while electromagnetic fields must be calculated self-consistently based on the distribution of charged particles. These simulations help scientists understand how electromagnetic organization emerges from the chaotic interactions of billions of individual particles. The beauty of Saturn's spokes lies not just in their visual impact, but in what they reveal about the hidden electromagnetic architecture of planetary systems. These ghostly features demonstrate that magnetic fields can create temporary order from chaos, organizing matter in ways that pure gravity cannot achieve. They show how electromagnetic forces, often overshadowed by more obvious gravitational effects, play crucial roles in shaping the structure and evolution of planetary ring systems. Jupiter's electromagnetic chaos, rather than representing a failure, shows us the normal state of affairs around magnetically active planets. Saturn's ability to maintain organized electromagnetic structures reflects the delicate balance of conditions required for complex ring phenomena. Another aspect of the cosmic lottery that has made Saturn's rings possible while leaving Jupiter disappointingly bare. The electromagnetic story of planetary rings reminds us that the universe operates through the interplay of fundamental forces, each contributing to the structures we observe. Saturn's spokes exist because electromagnetic forces found a way to organize matter temporarily, creating ephemeral beauty that bridges the gap between the microscopic world of charged particles and the astronomical scale of planetary systems. This electromagnetic choreography adds another layer of complexity to the already remarkable story of why Saturn wears a crown of rings while Jupiter remains unadorned. Chapter 7. Temporal Evolution. Saturn's rings exist in a state of constant change, caught in a cosmic death spiral that will eventually erase one of the most beautiful structures in our solar system. Every second, roughly 10,000 kilograms of ring material, equivalent to about 12 automobiles, rains down into Saturn's atmosphere, gradually depleting the magnificent system we're privileged to observe today. This ongoing destruction, combined with evidence for the ring's surprisingly recent formation, reveals a sobering truth. We exist during a brief cosmic moment when gravitational accidents have created temporary beauty in our solar system. The realization that Saturn's rings are temporary came as a shock to astronomers who long assumed these structures were permanent fixtures of our solar system. Early calculations suggested ring systems should be stable for billions of years, evolving slowly through gentle collisional processes that gradually spread material outward through gravitational interactions. The discovery that Saturn's rings are actively being destroyed and were formed relatively recently revolutionized our understanding of planetary ring evolution. Multiple processes contribute to ring material loss, each operating on different timescales and affecting different components of the ring system. The most dramatic is ring rain, charged ring particles that get caught in Saturn's magnetic field lines and spiral down into the planet's atmosphere. This process was directly observed by Cassini during its final plunge between Saturn and its rings, measuring the composition and quantity of infalling material with unprecedented precision. The ring rain phenomenon occurs because tiny ring particles become electrically charged through interactions with solar radiation and Saturn's magnetosphere. Once charged, these microscopic grains can be picked up by magnetic field lines and guided along complex trajectories that eventually intersect Saturn's atmosphere. The process is most effective for the smallest particles, those in the micron size range that can be easily accelerated by electromagnetic forces. Larger ring particles face their own destruction mechanisms. Atmospheric drag affects particles in the innermost ring regions, where Saturn's extended atmosphere creates enough resistance to gradually slow orbital motion. As particles lose energy to atmospheric friction, they spiral inward on ever-tightening orbits until they burn up in Saturn's dense atmosphere like meteors, contributing to the chemical composition of Saturn's upper atmosphere. Meteorite bombardment provides another pathway for ring destruction. When interplanetary debris impacts ring particles, it can vaporize both the impactor and portions of the target particle, creating hot plasma that escapes the ring system entirely. Large impacts can also scatter debris into unstable orbits that either impact Saturn or get ejected from the system. This process not only removes material, but also darkens remaining particles by adding rocky contaminants to their icy surfaces. The timescales for these destruction processes paint a sobering picture of ring longevity. Current estimates suggest Saturn's rings will lose roughly half their mass over the next 100 to 300 million years, depending on which destruction mechanism dominates in different ring regions. This timescale is remarkably short compared to the 4.6 billion year age of the solar system, confirming that we're witnessing the rings during a brief phase of their existence. But ring destruction isn't the only temporal story. The evidence for recent ring formation is equally compelling. The relative youth of Saturn's rings, estimated at 100 to 400 million years, based on their current mass and observed destruction rates, suggests they formed during the age of dinosaurs on Earth. This recent formation explains many puzzling features of the ring system that would be difficult to understand if the rings were ancient structures. Young rings naturally explain their high reflectivity and pure ice composition. Ancient rings would have accumulated substantial amounts of dark material from billions of years of meteorite bombardment, gradually darkening until they became nearly invisible. The bright, pristine appearance of Saturn's rings indicates they haven't had time to accumulate significant contamination, supporting the young age interpretation. The organizational complexity of Saturn's rings also supports recent formation. Ancient ring systems would have reached a state of maximum entropy, uniformly spread material with little structure or organization. The intricate gaps, density waves, shepherd-moon interactions, and electromagnetic phenomena we observe suggest a system that hasn't had time to evolve to gravitational equilibrium. These features indicate ongoing dynamical evolution from initial conditions established by recent moon destruction. Jupiter's sparse ring system demonstrates what happens when destruction processes operate without substantial recent replenishment. Jupiter's rings consist entirely of material continuously supplied by ongoing meteorite bombardment of its inner moons, with destruction processes removing material on timescales of thousands to hundreds of thousands of years. This balance creates a steady-state system with very low material density, essentially an equilibrium between supply and destruction. The contrast between Saturn and Jupiter highlights the importance of formation events in determining ring system characteristics. Saturn benefited from a massive recent injection of ring material that overwhelmed destruction processes and created dense structures that could evolve complex organization before being depleted. Jupiter never experienced such an event, leaving it with only the sparse material that ongoing processes can maintain. Understanding ring temporal evolution has profound implications for interpreting ring systems throughout the universe. Spectacular ring systems like Saturn's represent brief phases in planetary evolution when recent catastrophic events have created dense material populations that haven't yet been destroyed by various loss processes. Most of the time, planets either lack rings entirely or possess only sparse systems maintained by ongoing low-level processes. This temporal perspective makes Saturn's rings even more precious from a scientific standpoint. We're observing a transitional state between the catastrophic formation event and the eventual return to a ringless or sparsely ringed condition. The ring system serves as a natural laboratory for studying planetary formation processes, gravitational dynamics, and electromagnetic effects under conditions that may have been common in the early solar system but are rare today. The seasonal evolution of Saturn's rings adds another temporal dimension to their story. Saturn's 29.5-year orbit around the Sun creates seasonal changes in how sunlight illuminates the rings, affecting their appearance and potentially their dynamics. During equinox periods, when the rings are edge-on to the Sun, they become nearly invisible from Earth, highlighting their extreme thinness while creating optimal conditions for electromagnetic phenomena like spoke formation. Recent computer simulations have revealed the complex interplay between ring formation and destruction processes. Models suggest that ring systems undergo cycles of formation, evolution, and destruction driven by the chaotic orbital evolution of moon systems. Occasionally, gravitational interactions drive moons to destruction, creating dense ring systems that then gradually fade away over hundreds of millions of years until the next catastrophic event. These simulations help explain why ring systems are rare among the planets in our solar system. Most of the time, planets exist in the spaces between formation events, either completely ringless or sporting only tenuous systems maintained by ongoing processes. Dense, Spectacular ring systems like Saturn's require the recent occurrence of catastrophic moon destruction combined with environmental conditions that allow the resulting debris to survive and organize. The study of ring temporal evolution also provides insights into the history of our solar system. The relatively recent formation of Saturn's rings suggests that large-scale dynamical evolution continues in planetary systems, billions of years after their initial formation. Moon systems remain dynamically active, occasionally undergoing catastrophic reorganizations that can dramatically alter planetary appearance. This dynamical activity implies that the current configuration of our solar system is not permanent. Future gravitational interactions may drive other moons to destruction, potentially creating new ring systems around planets that currently lack them. Conversely, the gradual migration of moon systems due to tidal forces may eventually clear existing ring material and return ring planets to ringless states. The temporal story of Saturn's ring serves as a reminder of the transient nature of cosmic beauty. Like supernova, planetary auroras, and comet apparitions, ring systems represent temporary displays of natural magnificence that grace our universe for brief periods before fading into history. Saturn's rings remind us that even the most spectacular cosmic phenomena are subject to the inexorable forces of change and entropy. Understanding these temporal processes helps us appreciate the remarkable coincidence of our existence during Saturn's ringed phase. In the deep future, when human civilization has perhaps spread throughout the solar system, Saturn will appear as just another gas giant, lacking the spectacular crown that makes it one of the most beautiful objects visible through small telescopes today. Future astronomers will study Saturn's atmospheric composition and moon system dynamics to infer that rings once existed, much as we study the chemical composition of asteroid belts to understand the violent history of planetary formation. The temporal evolution of ring systems ultimately reveals the dynamic nature of our solar system. Far from being a static collection of planets following eternal orbits, our cosmic neighborhood continues to evolve through gravitational interactions that occasionally produce spectacular but temporary displays of natural artistry. Saturn's rings exist because we're fortunate enough to live during one of these rare interludes when destruction and creation have combined to produce cosmic beauty on an astronomical scale.